Hello everyone, in this video we're going to do an introduction to graphs. So what is a graph data structure? A graph data structure is a graph's nonlinear data structure that consists of vertices, or you could call these vertices nodes, and edges, and which form a relationship to each other, or a linking pair of vertices. So what I'm saying here in simple terms is that 1, 2, and 3, and 4, and 5 are called vertices slash nodes. You could call them vertices or nodes. And what's linking these vertices slash nodes are called edges, these lines over here. That's it. And all right, that's a graph data structure in simple terms. Now, what application use of the graph data structures? It's used in social networking to show the relationship between you and your friends in a graph data structure. Networking in the IT infrastructure, right over here, you could see that a graph data structure would be really useful to show the relationship between the server and the company's computers and the company's IT infrastructure. In maps, to help you find the shortest path to your destination, something like Google Maps. Dating apps to help you find love, find the best match in the graph data structure, the best or possible match for you in your area. Machine learning there's a lot of data in machine learning, and you could storing them in nodes or vertices, sorting them out. Something like TensorFlow. Ride sharing app to help the driver get to your destination using the shortest path. And many more applications. So how is a graph represented? This is an undirected graph. In an undirected graph, you can go to, there's no specific direction, so I can go from 1 to 3, 3 to 1, 4 to 1, 1 to 4, 2 to 1. There's no specific direction I have to go. And 0 represents there is no path. I cannot, no outward line or edge. So 1 represents an edge. So this is an adjacency matrix over here. So 0 represents there is no edge. 1 represents an edge. As you can see for this, and right over here in the 1 row, it represents the 1 vertices slash node. The 2 row over here represents the vertices slash node. The 3 node represents the vertices slash node, and the 4 row represents the vertices. Okay, and as you can see for at 1 has an edge connected to 2. So we put 1 here. 1 also has an edge connected to 4. So we put it 1 here, and 1 has an edge connected to 3. So we put 1 here. 1 does not have an edge connecting to 1. That's why it's 0. If it did, it would be a loop. So 2 has an edge connecting to 1. So we put 1 here. Does 2 have an edge connecting to 2? No. Does 2 have an edge connecting to 3? Yes. Does 2 have an edge? So that's why we put 1 here. Does 2 have an edge connecting to 4? No. So we put 0. And we keep going on. Let's do it for 3. 3 has edges connecting to all vertices except itself. And 4 only has 2 edges, and it's connecting to vertices 1 and vertices 3, and we put 1 to represent the edge. And 0, does it have it to 4 have a vertices, edge connecting to 2? No, so we put 0. And does it have an edge connecting to itself? No, so we put 0 on 4. And this will be represented, an adjacency matrix will be represented in a 2D array in most programming language. So what's an adjacency list? It's a linked list. And you just put the nodes in the linked lists. So the linked list, for example, here at 1. So this represents the 1 vertices. In the 1 vertices, we put the nodes that are connected to 1. So which is 2, 3, and 4. And the same for 2. We put the nodes that are connected to 2, so which is 1 and 3. And what's connected to 3 is 1 and 2 and 4. 3 is not connected to itself, and you can see it 4, 1, and 3. You could just take a look at it. You can see the relationship in the adjacency list and the adjacency matrix. All right, let's get into directed adjacency matrix. So in this graph over here, you can see there's direction. There's arrows pointing to the vertices. So as you can see at 0, does the 0 have a vertices? I mean, an edge, a directed edge pointing to itself. So does 0 have a directed edge pointing to itself? No. Does 0 have a directed edge pointing to 1? Yes, you can see it right over here. Does 0 have a directed edge pointing to 2? Yes. Does 0 have a directed edge pointing to 3? No. So what we represent the edges here, like in the previous slide, with 1 and 0. And if it doesn't have an edge, we put a 0. All right. Does 1 have a direct path to 0? No. Does 1 have a direct path to 0? No. They're connected, you can see right over here, but there's no direct path. So if there's no direct path from 1 to 0, we put 0 to represent there is no direct edge. Does 1 have a direct edge to itself? No. Does 1 have a direct edge to 2? Yes, we put 1. Does 1 have a direct edge to 3? No. So we put 0. And this, okay, we'll go over here. Does 2 have a direct edge to 3? Yes, we put 1 at 2, 3 in the 2D matrix, or the adjacency matrix. So we go 2, 3, we put 1 here. You see there's a relationship, 2, 3. Does 2 have a relationship, a directed relationship with 0? No. So we put 0. There's no direct edge from 2 to 0. Is there a direct edge from 3 to any of the other vertices? No. But there's only a direct edge from 2 to 3. So this is an undirected weighted graph. Here the edges have value. So in the previous slides, we put 1 to represent the edge. We only put 1 there if the edge has actually no weighted value. But now the edges do have weighted value. So let's look here. 0 to 1. And this is undirected. There is. So right over here, the edge has a value of 2. And these weighted graph values, or these weighted values, can represent something, let's say, kilometers. It could represent any units. We're just going to not represent any units. We're going to represent numbers. So from 0 to 2, the weighted value is 3. Okay, 1 to 2, 15. 2 to 4, 13. 3 to 4, 9. You get the pattern. So if you want to, if in an unweighted graph with 1s and 0s, if you want to make it weighted, just replace it with numbers, the weighted value numbers. And similar to unweighted graphs, 0 represents nothing. No edge. So this is an adjacency list and adjacency matrix. You can see adjacency list, right? This is how you would do it in a directed graph. This is how you represent an and you can see there's no weighted edges value in the edges, so this is an unweighted graph, but this is a direct graph. So right over here, you can see in the adjacency list the representation for this graph, and you can see in the matrix, adjacency matrix, the representation for this graph. All right, weighted directed graphs. So 2 slides before we had weighted undirected graphs. Now we have weighted directed graphs, as you can see over here, and this is represented in the code of Python 1.4.2.1 has a in the JC weighted list of 5. We put 5 here. For 1, put 5, and then we put the weighted 4.2.1. And for 3, you could see that it has 4.4. For 3, go 4, and we have the value 4. So right over here, you could see 1, 4, it's going to 1, and then on the second value, second index of the list, we put the weight. So first value, we put the destination, and the second value, we put the weight. Let's go at 1. So 2, 1 is going to a direction of 2, and from 1 to 2, we put the weighted value, which is 1. 1 to 3, we put the weighted value 1, as you can see right over here. Now from 2 to 3, we put the destination and the weighted value, and 3 to 4, we put the destination, the directed destination, and then the weight. As this is the representation in an adjacency list in a language like Python or JavaScript. This looks like Python code. Adjacency matrix, as you can see over here, for this will be 1, so you can see that 1, and then this is going to be 3, 1, we just put the weighted value, and then for 2 to 3, we just put the weighted value 3, and then from 3 to 4, we just put the weighted value, which is 4, and from 4 to 1, we just put the weighted value here at 5. All right, let's talk about the types of graphs. So we have undirected and directed graph. In undirected graph, I don't have to go in a specific direction. And we talked about undirected, and directed graphs in the previous slides. For example, starting from node 3 in an undirected graph, I can go 3, 5, 3, 1. Let's go to a directed graph. Let's start from 3. In a directed graph, I can go 3, 1, but I can't go to 3, 5, as you can see from the arrow here. All right. So undirected graph, there is no direction. In directed graph, there is direction. You have to follow the directions. So, example, in the directed graph, I can go 3, 1, but from 1, I can't go to 4 or back to 3. But if I start from 5 in a directed graph, I go 3, 5, 1. But if I go back to the undirected graph, I can go 3, 5, 1, 4, and then back to 5. Again, undirected graph, no direction. Directed graph, there is you have to follow a specific direction on the edge. All right, let's talk about connected graph and disconnected graph. So a connected graph is where you can, from one node, I can visit all the other nodes. So what I mean is from one node, I can visit any node on the graph. So, for example, from 5, I could visit 4, and then from 4, I could visit 3. And 3, let's say I start from 3, I could visit all the nodes. If I start from 5, I could visit all the nodes. In a disconnected graph, if one node is unreachable because there's no connection in the edges, therefore it makes it a disconnected graph. For example, if I start from 5, I can get to 3. But if I start from 5, can I get to 4? No, because there's no edges connecting them. Therefore, it makes it a disconnected graph. A completed graph is when the edges are connected to all the nodes in the graph. That makes it a complete graph. For example, from B, there's an edge connecting it to D. There's an edge connecting it to E, C, and A. And the same applies to D and E and C. You can see that the edge is connecting to all the nodes in the graph. And then there's cycle graph and there's cyclic graph. In a cycle graph, the cycle forms itself. You can see it's just one big cycle. As you can see from 3, if I go visit all the nodes, I'm back at 3, where I started. From 5, if I visit all other nodes, the cyclic graph has no, it's at least containing one cycle. The graph is not a cycle itself. The whole entire graph is not a cycle itself in the cyclic graph. All right. So just remember that in a cycle graph, the graph is a cycle itself. In a cyclic graph, it has at least one cycle in it. But the graph is not a cycle itself in a cyclic graph. Now, how do I traverse a graph? So we're going to talk in the next video, breadth first search, and then depth first search. All right. And thank you for watching, and I hope you guys learned something about graphs today.